For millennia, we've looked to the sky, mesmerized by the effortless flight of birds. Now that fascination is fueling a revolution. While the drones we know today are mostly buzzing quadcopters, a new generation of flying machines is being engineered to not just fly, but to fly like a bird. This isn't about making a drone that simply looks like a bird. It's about fundamentally reverse engineering 3.8 billion years of evolution to create robots that are quieter, more efficient, and more agile than anything we've built before. This is the world of avian-inspired robotics. Before you can build a robotic bird, you have to understand what makes a real one fly. Unlike an airplane, which has separate parts for lift and thrust, a bird does it all with one elegant mechanism, the flapping wing. A bird's wing is an airfoil, a curved surface that generates lift based on pressure differences, just like an airplane. But the real magic, and the greatest challenge for engineers, is in the unsteady aerodynamics of the flap itself. The downstroke is the power stroke. The wing moves downward and forward, pushing air back to generate both lift and thrust. The feathers lock together, forming a solid, powerful surface that can generate forces up to twice the bird's body weight. Then comes the upstroke, or recovery stroke. Here, efficiency is key. The bird partially folds its wings, flexing its wrist and elbow joints. The primary feathers at the wingtips can even separate, like opening Venetian blinds, allowing air to pass through. This minimizes resistance as the wing is brought back up for the next power stroke. This constant change in wing shape, angle, and even porosity is a level of complexity that traditional aerodynamics struggles to model. Nature has also created a whole catalog of wing designs. Sparrows have short, rounded wings for incredible maneuverability in cluttered forests. Falcons have long, thin wings for high-speed pursuit. Albatrosses have long, narrow wings that are hyper-efficient for gliding over oceans. And eagles have broad wings with slotted tips that act like winglets on an airliner, helping them soar on thermals with minimal effort. Engineers are drawing inspiration from all of these designs to create drones for specific tasks. But translating this biological genius into a machine is an immense challenge. First, there's the actuation problem, mimicking muscles. A bird controls its wings with a complex system of muscles and tendons, allowing it to bend, twist, and rotate at multiple joints. Replicating this with motors is a huge hurdle. Early robotic birds used a single motor to flap both wings together, which severely limited their agility. A major breakthrough came with a project called Raven, which used two programmable motors, one for each wing. This independent control was a game changer, allowing the robot to perform aerobatic maneuvers like rolls and flips by varying the flapping of each wing, just like a real bird. But the more motors you add to increase maneuverability, the heavier the drone becomes. This leads to a vicious cycle. More complexity means more power is needed, which means a bigger battery, which adds more weight, requiring even more power just to get off the ground. Next is the material problem. Birds are masters of lightweight design. Their bones are hollow but strong, and their feathers are an engineering marvel. Lightweight, flexible, and capable of tiny adjustments. Engineers can't just use standard metals. They turn to advanced materials like carbon fiber, which has an incredible strength-to-weight ratio. The famous SmartBird robot, modeled on a herring gull, has a nearly 2-meter wingspan, but its entire structure weighs only 450 grams. But the biggest material challenge is recreating the feather. Feathers aren't just passive surfaces. They lock together on the downstroke and separate on the upstroke. Some projects like the PigeonBot from Stanford University took a novel approach. They used real pigeon feathers on their robot's wings to study these properties directly. Their research revealed that birds control large groups of feathers with simple movements of the wrist and discovered that the tiny hooks on feathers act like directional Velcro, locking them together when needed. Then, of course, there's the power problem. Flapping flight is energy-intensive. For most flapping-wing drones, the battery is the biggest limitation on flight time. Researchers are tackling this by designing more aerodynamically efficient robots, creating hybrid flight modes that switch between flapping and energy-saving gliding, and even integrating flexible solar cells onto the wings. The Raven 3 was a key example, demonstrating it could recharge its own batteries using sunlight. But perhaps the most complex challenge of all is creating the brain of the bird. A living bird's nervous system makes countless instantaneous adjustments. Replicating this level of autonomous control is the holy grail. Traditional control methods often fail because the aerodynamics of flapping flight are too complex and unpredictable to be captured in a perfect mathematical model. This is where artificial intelligence comes in. Researchers are using reinforcement learning, a powerful AI technique where a controller learns through trial and error in a computer simulation. It gets rewards for good decisions and penalties for bad ones, essentially teaching itself how to fly. AI has been used to discover optimal flapping patterns to maximize lift, achieve stable flight, and even perform complex aerobatics. Some are even using brain-inspired spiking neural networks, which more closely model how biological neurons work, to create more robust and faster flight controllers. These theoretical challenges are being met with practical ingenuity in labs all over the world. A few projects stand out as major milestones. Unveiled back in 2011, Festo's SmartBird is still a landmark. Modeled on a herring gull, it can take off, fly, and land autonomously just by flapping its wings. Its most revolutionary feature is called active articulated torsion. The wings don't just flap up and down. Motors inside actively twist them during the flap cycle. This elegantly couples lift and propulsion, achieving incredible energy efficiency. Then there's Stanford's PigeonBot, the biohybrid robot with real feathers. While it used propellers for thrust, its feathered wings were used for steering, and the project provided unprecedented insights into how birds morph their wings and the critical role of the feathers themselves. At the EPFL in Switzerland, researchers have developed the Lys Eagle, a sophisticated drone with morphing wings and a tail. Using a form of AI, the drone can autonomously adjust its wing and tail shape during flight to maximize energy efficiency at different speeds, achieving gains of up to 11.5%. It's a huge step towards truly adaptive avian drones. Another EPFL project, the Raven, tackles a different aspect of bird versatility: movement on the ground. Inspired by crows, it has articulated legs that allow it to walk, hop over obstacles, and perform an energy-efficient jump-assisted takeoff, making it perfect for deployment in rugged terrain. So where is all of this heading? The future of avian robotics is focused on greater autonomy, efficiency, and swarm intelligence. Just as birds fly in coordinated flocks, the future of drones lies in swarms. Imagine fleets of flapping-wing drones working together on large-scale missions, all without a central leader. In precision agriculture, a swarm could cover hundreds of acres, monitoring crop health and targeting pests with pinpoint accuracy. In a search and rescue operation, a swarm could rapidly map a disaster area, with individual drones peeling off to investigate tight spaces that a single, larger drone could never access. The unique advantages of bird-like drones are also opening up entirely new applications. Their quiet, naturalistic flight is far less disturbing to wildlife than the buzz of a quadcopter, allowing for more accurate population monitoring without stressing the animals. For military or law enforcement, a drone that looks and flies like a common bird offers the ultimate camouflage for stealth surveillance. And in cities, their agility makes them perfect for navigating urban canyons for tasks like infrastructure inspection. The journey to engineer avian flight is a testament to the elegance of the natural world. For centuries, we dreamed of flying like birds. We eventually surpassed them in speed and scale, but now we're turning back to them to learn the secrets of agility and efficiency that our machines still lack. With each breakthrough, we move closer to a future where our skies are populated not just by buzzing multirotors, but by a new class of silent, graceful, and intelligent flying machines. The dream of flying like a bird is no longer just poetry, it's becoming an engineering blueprint.